All right, guys, welcome back from the break. Let's get started.
30 years ago, space was considered a vacuum, except for a curious clue, the tail of a comet. Regardless of the direction it traveled, its tail always pointed away from the sun. A mystery unexplained until the discovery of the solar wind.
All right, so tail of a comet always points away from the sun. So the question is why? Newton wondered. Right? So this is a question that Newton himself came up with. You notice that the tail of a comet always points away from the sun. So what does it mean? What does it say about the nature of light? So far, we decided that the nature of light has a wave nature, right? So that's the direction that we end up going. Newton thought not so much. Newton thought that the light probably had a particle nature. All right, so if you're wondering why, here's the reason why. The tail of a comet is composed of particles, right? You got dust particles, you got ice particles. The particles, through collisions, will transfer energy. Through collisions, they will transfer energy as well as motion. Waves, while they transfer energy, they don't necessarily transfer motion in the initial direction of the motion of the wave. For example, if it's a compression wave, what happens? If it's a longitudinal wave, these particles will be vibrating back and forth. They're not going to get pushed away. They will just vibrate back and forth. If it's a transverse wave, what happens is the wave is going through the particles will just go up and down. They're not going to get pushed in the direction of the light rays, let's say. All right, so which means that as far as Newton was concerned, the light had to be composed of particles. Particles through collisions can transfer momentum or motion. So that's the thinking that Newton had at the time. While the competing view is the one that we looked at, that's the Huygens view. Huygens said that the light is composed of waves. And so far, the evidence suggests that the light is composed of waves. But Newton has an argument. Remember the wave nature? Wave is a traveling disturbance. While it's traveling, it carries energy. And also we know that the waves will interfere. They will cause an interference pattern. You can get a constructive interference pattern where the amplitude becomes maximized, or you can get a destructive interference pattern where the amplitude is going to become minimized, or it can simply cancel. All right, so we talk about electromagnetic waves, and then we will continue talking about electromagnetic waves today. Last time we've done it conceptually. This time we will do a little bit more mathematically. So electromagnetic waves will have an electric field component, which is E, and then they will have a magnetic field component, which is B. And they're going to be traveling at the light speed. All electromagnetic waves travel at the light speed.
A wave is a disturbance that propagates from one place to another. And no matter whether they're electromagnetic waves, or water waves, or any other kind of waves, all waves have certain properties in common. For example, a wave's frequency times its wavelength equals its speed. But mechanical waves can be longitudinal or transverse, while electromagnetic waves are always transverse, and in empty space, they always travel at the speed of light. But although they always have the same speed, they can have vastly different frequencies and wavelengths. And in doing so, these waves go so far as to create the entire electromagnetic spectrum.
Okay, so let's go through the electromagnetic wave spectrum one more time. Okay, so the lowest portion is going to be the radio wave frequency range. It's going to be between 10,000 to 100 million cycles per second. Okay, guys, I'm going to skip over the multiple choice. We've already done that. All right, so the next range is going to be microwave frequency range. So it's going to be 100 million to a trillion cycles per second. And then once you get over a trillion cycles per second, between a trillion to 100 trillion cycles per second, so this is going to be the infrared, meaning heat. And then region above it is going to be visible light. When things are heated, they will glow, so you end up getting visible light, which is going to be caused by the electrons jumping inside the atoms, known as quantum jumps. Next frequency range is going to be ultraviolet. It's even a higher frequency range. All right, so discharge of an electrical arc is going to be responsible for it. The region above it, the X-rays, even higher frequency. Obviously, as the frequency goes up, the wavelength is going to get shorter and shorter.
Röntgen found that when certain objects like coins or steel weights were placed between the plates and the rays, they would imprint bizarre shadow images. Röntgen knew he was producing a new kind of ray, and amazingly, it was capable of penetrating opaque objects such as the steel barrel of his hunting rifle. Finally, Röntgen held his hand between the rays and the fluorescent screen. What he saw was shocking. Wilhelm Röntgen was staring at the skeletal shadow of his own hand.
It is rumored that when he finally, after a couple of weeks, told Bertha she better come and look, and Bertha was getting a little bit curious or annoyed, but he hadn't been eating his meals. He would rush right back to the lab whenever he did, and he finally said, "You're not going to believe this."
Röntgen placed Bertha's hand in front of the ray and captured the haunting image of her wedding ring floating upon a bony finger.
And it is said that she said, when she saw her hand, "I have seen my death." Because up until this time, no one ever saw bones unless they were bones of dead people.
A month later, Röntgen submitted a handwritten account of his discovery, along with a photo of the X-ray image, to the Physico-Medical Society of Würzburg. He identified the ray as X for unknown. Within weeks, both Röntgen and the X-ray were worldwide phenomena. In 1901, Röntgen's discovery would be awarded with the first Nobel Prize ever granted in physics. His mysterious X-rays were soon recognized by physicists for what they really were: electromagnetic waves with a length about 1/1000th that of visible light. But to the Western world, they were much more. Within months of their discovery, X-rays would impact healthcare, the legal system, and forensics. They would be seen as everything from a tool of the occult to a novelty amusement, and they would fire the opening shot of a social and sexual revolution.
And the highest frequency region is the gamma ray region. All right, so the question is, an electromagnetic wave is generated by what? Okay, so based upon all the discussions that we had at this point, it's a trial and error. Okay, so you don't quite know the answer, but you almost know the answer. So the question is, which one? Okay, so only a charge moving in a straight line, forget it. It's not going to be able to generate, it's not going to generate an electromagnetic wave. If the charge is moving in a straight line, it just creates a circulating creates a circulating magnetic field, right? The charge should be moving up and down, up and down, up and down in order to generate an electromagnetic wave. The electric field component is going to be going up and down, driving the charge up and down. And the electric field component is going to cause a circulating magnetic field component. As the strength of the electric field changes, it's going to change the strength of the magnetic field. And when the strength of the magnetic field changes, it generates the electric field component. So any variation within the strength of the electric field component causes the magnetic field component. And any variation within the strength of the magnetic field component is going to be responsible for the electric field component. And everything is going to get started if there is a charge. If you move a charge up and down a number of times per second, the motion of the charge is going to create the electric field component, and the motion of the electric field component is going to create the magnetic field component. So this is what you're looking for, the motion of the charge. So what comes closest to describing this motion? All right, so this is called accelerated motion. Object is speeding up and slowing down and changing direction, and speeding up and slowing down and changing direction. Speeding up and slowing down and changing direction. All right, speeding up is acceleration, slowing down is acceleration, changing direction is acceleration. So which means that any accelerating charge is going to cause an electromagnetic wave. Frequency of that acceleration, the number of times the charge goes up and down, becomes the frequency of the electromagnetic wave. So the best answer is.
As a matter of fact, only when electromagnetic waves have a wavelength in the narrow range from 4 to 700 nanometers are the waves visible light. That is the spectrum from red to violet. Even shorter wavelengths, called ultraviolet light, are radiated by the sun. Though these invisible rays are dangerous to living things, they're absorbed and rendered harmless by the ozone in the Earth's atmosphere. Shorter still are X-rays, with wavelengths the size of atoms. And finally, gamma rays, with the shortest wavelengths of all. Gamma rays, with wavelengths as tiny as the atomic nucleus itself, are created by nuclear reactions. Longer wavelengths, extending to visible light and beyond, can be created or absorbed from one energy state to another. Beyond visible light, there's infrared. With wavelength longer than red light, infrared radiation can be detected only by the heat it deposits. The universe is suffused with long wavelength radiation, seen as the cooled remnants of the Big Bang that started it all. That includes not only infrared radiation, but also microwaves. Microwaves are the first part of the spectrum, whose frequency is low enough to be generated by human-made, alternating current electronic circuits. The universe is likewise full of radio waves. Centimeters, meters, or even kilometers in length, radio waves complete the electromagnetic spectrum.
All right, so Erstat in 1819 discovers that the current, the electricity, generates magnetism. So the magnetic field is going to wrap itself around the current wire. And Faraday in 1830 or 31, he discovers that if you vary the strength of the magnetic field inside a loop, that's going to generate current. All right, so in Faraday's mind, here's the state in place. All right, so you get an alternating current generator. This piece of wire is hooked onto an alternating current generator. So the current is going up and down, up and down. So what's driving the current up and down is the electric field. And then the electric field is going to get radiated away at the light speed. So that becomes the electric field component of the electromagnetic wave. The current generates magnetism. The current generates a circulating magnetic field. Now, what's generating the circulating magnetic field is not the current as far as Faraday is concerned. It's what drives the current. That's the electric field. So the electric field is what generates the circulating magnetic field. So as the electric field starts to move away because its value is changing, and it's going to cause a circulating magnetic field around it. So the field is going to end up wrapping itself around the electric field. As the strength of the electric field keeps changing, what happens? The strength of the magnetic field is going to keep changing at the same time. So any variation within the strength of the magnetic field, any variation within the strength of the electric field generates the magnetic field component. Any variation within the strength of the magnetic field generates the electric field component. As a result, you end up getting the self-propagating field, which is known as the electromagnetic field. All right, so Faraday is the guy who was able to formulate Maxwell is the guy who was able to formulate what Faraday came up with in his mind. The first one is the Gauss law. We discovered that. So the electric field is caused by a net charge within the Gaussian region. So this is the area of the Gaussian region. There's no magnetic charge. That's the reason why within the Gaussian region, if you're looking at the magnetic field, you're not going to be able to find a magnetic charge. If you vary the strength of the magnetic field within a certain region, it's going to cause a circulating electric field. Obviously, if you have a loop of wire there, there's going to be current within that wire. On top of that, this is what Erstat discovered. The current causes a circulating magnetic field. And this is what Faraday was just talking about. The Faraday kept saying, hey, if you vary the strength of the electric field within a certain region, changing the strength of the electric field is also going to cause a circulating magnetic field, just like the current does. All right, so this is Faraday's contribution. If you vary the strength of the magnetic field within a certain region, it causes a circulating electric field. This is known as the Faraday's law. And also in Faraday's imagination, if you do the opposite, this time if you change the strength of the electric field within a given region, it's going to cause a circulating magnetic field. So any variation within the strength of the magnetic field causes a circulating electric field. Any variation within the strength of the electric field is going to cause a circulating magnetic field. When combined, it turns into an wave. All electromagnetic waves will travel at the light speed. Okay, it comes out of the map, and this is at the constant speed.
Your microphone is messed up right now.
Okay. Here's our stuff, guys. Hold on. Okay, is it working better?
Yeah, it's good.
Awesome. All right, so that little thing, remember those constants, epsilon naught, this is the space permittivity constant. V naught is known as the space permeability constant. And I said somehow they set a speed limit in terms of how fast the electric as well as the magnetic fields can travel in space. In essence, that thinking was correct. As it so happens, electromagnetic fields can only travel at a given speed, a constant speed of light in a vacuum. So this is how fast they travel. All right, so Maxwell publishes his findings, more like his theory, not his theory, Maxwell's theory, his own theory, 1865, 150, almost 60 years ago, obviously. And one of the things which is intriguing is obviously all electromagnetic fields are traveling at the light speed. Faraday comes up with the idea, Maxwell comes up with the formulation. When he's doing the formulation, he knows that if you're describing speed, you have to always describe it relative to something, some stationary point. In this case, this stationary point is P. So relative to this point, light is traveling at the light speed. All right, so the question is, there's nothing in the universe which is stationary. Everything is moving. Everything is moving. I mean, while you're sitting, you're thinking, I'm stationary. Yes, you are stationary relative to the floor, but you got to remember that you're still part of the Earth reference frame, which is spinning on its axis, right? Like 1,000 miles per hour. And Earth is also moving about the sun, 80,000 miles per hour. Okay, the number is probably made up. I kind of recollect that it's close to 80. And the sun is not stationary. It's moving relative to the center of the galaxy. The center of the galaxy is not stationary. It's moving relative to other galaxies. All right, so everything is in motion. So the question becomes, light moves at the light speed relative to what? You have to have a reference point. And all of a sudden, and then also the second question is, if it's a wave, what is the medium that it's disturbing? Now we got that question as well. Because the wave is just traveling disturbance, right? And what determines how fast the wave is going to travel is the medium itself. And space, as far as a medium, it's not a good medium because there's nothing in it. When we say space, there's literally nothing. It's a vacuum of space. It's not made up of atoms. It's not made up of molecules. It doesn't have any tension that we could see. Tension of what? Tension of space. What's going to cause the tension? There has to be some kind of something which is connected to something else. It's a vacuum. It's not connected to anything. And all of a sudden, the physicists are forced to come up with the idea of ether. All right, this sounds like it's some kind of a weird argument, but this is essential in our understanding of what's about to happen. It's essential regarding the nature of light. If it's a wave, what is the medium that it's disturbing? So it can travel at the light speed. If it's a wave, with respect to what? In reference to what? It's traveling at the light speed. All of a sudden, physicists were literally forced to come up with a special medium for light. All right, so relative to ether, they said light travels at the light speed. And ether is your reference. It's your reference frame. It's a stationary reference frame for light. Relative to ether, light moves at the light speed. And ether has the proper characteristics, which allows the light to travel at the light speed. It's going to have the proper amount of tension. Okay, tension among what? We don't know, whatever the ether is made up of. And it's going to have the proper density. All right? Only light is going to be able to interact with ether, not matter. We can go right through ether without even noticing it. It permeates all space, and it's a medium for light, and only relative to ether, light is the only thing that travels at the light speed. All right, so it's a hypothetical medium that they came up with. Christian Huygens is the guy who proposed it. It made sense to Maxwell to use the idea. And all of a sudden, Einstein comes along and goes, wait a minute, it gets kind of confusing. He says, what if there's no ether? Leave it up to Einstein. He's 16 years old. He says, what if there's no ether? So does this mean that the light travels relative to in a reference point, regardless of the speed of that reference point? He says, does this mean that if I'm traveling at the light speed, light still travels at the light speed relative to me? Does this mean that I should still be able to see my reflection? All right, so young Einstein, he doesn't buy the argument of ether. He looks at it, he says, what if there isn't any ether? Because it didn't make sense to Einstein that there's a special medium for light so that the light could travel at the light speed. Now, all of a sudden, we got these weirdnesses. Okay, so light certainly behaves like wave, but then again, it doesn't do what waves do in a sense that the waves will need some kind of a medium for them to be able to travel at the light speed, obviously. And vacuum of space is no medium. There's nothing to disturb within the vacuum of space. Yet light still travels at the light speed all the way from the sun. But it requires a special medium. So the question is, what if
It is nothing
there's no such medium?
other than light itself. And nothing fascinated the young.
So that became the question that we will get to answer at some point. I think within a few weeks, but we'll get back to it. So it's, what if I'm traveling at the light speed?
Says you can't have static light.
Maybe Maxwell is wrong. Maybe if you catch up to light, it is static, Albert, like a wave next to a boat.
Imagine if I was sitting still and holding a mirror to my face. And the light travels from my face to the mirror, and I see my face.
Yes?
However, if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
That doesn't make sense.
Young Einstein was starting to realize that light was unlike any other kind of wave. Einstein was about to enter a surreal universe where energy, mass, and the speed of light intermingled in a way no one had ever suspected.
All right, so electromagnetic, if light is a wave, okay, so the definition of a wave is it's a disturbance that carries energy. Right? So when I say light, I mean the electromagnetic waves in general. All right, so electromagnetic waves will have two components. Get an electric field component, so get a magnetic field component. Half the energy is going to be carried by the electric field component, and the other half is going to be carried by the magnetic field component. All right, so this is the energy density of the electric field component. So this is the energy density of the magnetic field component. Okay, so the energy density of an electromagnetic wave. So this is the amount of energy which is going to be carried by the magnetic field component of the electric field per volume of the magnetic field component. And this is the electric field. This is the energy density of the electric field, which means that this is going to represent the amount of energy carried by the volume of the electric field component. And this represents the amount of energy carried by the volume of the magnetic field component. All right, so electromagnetic waves will have magnetic as well as the electric field components. So 1/2 of the energy is going to be carried by the magnetic field. One half of the energy density is going to be carried by the electric field component. All right, so this is the lowercase u. This represents the energy density. All right, so that's the amount of energy carried or stored per volume of the electric as well as the magnetic field components. All right, so this whole thing comes out of the definition of a wave. Remember, it's a disturbance that carries energy with it. That's what it is. So 1/2 of the energy is going to be carried by the magnetic field component. The other half is going to be carried by the electric field component. All right, so when you add up the energy densities carried by the electric and the magnetic field components, it's going to add up to the total energy that we got. So 1/2 of the energy density is going to be carried by the electric field component, and the other half is going to be carried by the magnetic field component. All right, so it kind of makes sense. So what that means is that energy density of the electric field component as well as the magnetic field components will be equal to each other. All right, so the energy density or amount of energy per volume carried by the electric field component is going to equal to the amount of energy per volume carried by the magnetic field component. All right, so those two formulas that we saw will be equal to each other. All right, this formula is going to equal to that formula. All right, and out of this, we will come up with something interesting. All right, so 1/2 will cancel, so that stuff is going to go away. Okay, so let's come up with an expression for the electric field component. So divide both sides by epsilon naught. And then what do? Take the square root of both sides. Okay, so this expression that you're looking at, 1 over the square root of these two constants, product of these two constants, this expression is the light speed. All right, so that's going to give you the light speed. Okay, so what that means is the electric field component is going to be light speed times bigger than the magnetic field or stronger than the magnetic field component of the electromagnetic field. So which means that the magnitude of the electric field is going to be light speed larger than the magnitude of the electric field component, or it's going to be larger than the magnitude of the magnetic field component. All right, so which means that the electric field component is going to be much stronger than the magnetic field component of the electromagnetic wave. All right, so this represents the amplitude. Remember, this thing, it could be a sine wave or cosine wave. So this thing is going to be going up and down, like a sine wave or a cosine wave or whatever. All right, so this is going to represent the amplitude, the maximum displacement of the electric field as well as the magnetic field components. So instead of using the maximum displacements, we can also use the RMS values for both of them. Okay, so based on the discussion that we just had, it caused a bit of a confusion because despite the fact that I put equal emphasis on everything that I wanted to say, okay, everything is fresh on your mind, so it's easy to get confused at this point. Okay, time, average, energy, we're talking about the energy density of the electromagnetic waves. All right, so the energy density of the electromagnetic waves is going to be equally divided between the electric and the magnetic fields. All right, so the strength of the electric field component is going to be much larger, light speed times larger than the magnetic field component. So don't get that confused with what we just discussed. All right, the other concept that we will discuss is the wave intensity, electromagnetic wave intensity. So what's intensity? Let's focus on that. All right, so the intensity is usually related to the amount of power intercepted by an area. It's the amount of power intercepted is known as intensity. All right, so obviously the power is being intercepted by some kind of a cross-sectional area. It's the amount of power intercepted is known as intensity. Power is how fast the energy gets transferred, how fast the energy is converted, how fast the work is done. So we have to clear that up a little bit. All right, so the energy carried by an electromagnetic wave is something that we discussed. All right, how fast the energy gets carried becomes power, and how much power is being intercepted becomes the intensity in essence. All right, so the intensity, everything is about definitions. That's the power per area. That's the amount of power intercepted by an area is known as intensity. So this capital S is going to represent intensity. P represents power. A represents area. All right, so the power is how fast the energy is transferred. All right, how much, in this case, U represents energy. It's not energy density. This is the total energy being transferred. So how fast the energy gets transferred per second per area. No, it's how fast the energy is transferred. So that's the amount of energy per time is your power. If you do a back substitution, which we will, so intensity becomes amount of power intercepted, or amount of power intercepted by an area, or how fast the energy is being intercepted by this area, or the amount of energy per second intercepted by this area. Everything is fine. So that's the interpretation that works. It's the same thing. I'm just giving it a little bit more clear expression. All right, so this represents the amount of energy. Okay, so I can express the amount of energy in terms of energy density. Okay, so lowercase u is the energy density. This is the amount of energy being carried. This is the amount of energy per unit volume. So I can express the amount of energy per unit volume times volume is going to give you this. So lowercase u represents the volume. This capital V represents the volume. Lowercase u represents the energy density. So we're trying to come up with a mathematical expression that's going to give us a much more concise mathematical expression for intensity that we're looking for. All right, so this is the area that's going to intercept the electromagnetic wave. So the electromagnetic wave is coming in at the light speed. All right, so this is the volume through which the electromagnetic wave is going to go through, or it's going to get intercepted. All right, so the base length is speed times time. Speed of light speed times time is going to give you the distance. All right, so this is the base length of the volume that you're looking at. And it's going to have this area. All right, so A is going to represent the area. So the volume of this is that we are looking at is going to be expressed in terms of the base, which is going to be C times T times the area is going to give us the volume, right? So this volume, we can just do a back substitution into that one. It can be expressed just like that. All right, so we end up expressing the amount of energy carried by the magnetic field, which is this, in terms of the volume density. All right, this is in terms of the energy density, which is lowercase u. So the energy density multiplied by the volume itself is going to give you the amount of energy being carried. So the volume is going to be expressed in terms of light speed and time. So that's going to give you the base of the volume times the cross-sectional area that's going to be intercepting the electromagnetic wave. All right, so we can do a back substitution into that formula. Immediately we'll get rid of the light term. So the time is not going to matter. The area is not going to matter. We end up getting a cancellation there. All right, so we came up with an expression for the energy density. That's the amount of energy carried by the per volume of the electromagnetic field at the light speed. Is going to give you the intensity of the electromagnetic wave. All right, so this is the intensity. So this is the amount of power intercepted becomes the intensity of the electromagnetic field. That's it. The lowercase u can be expressed in terms of its electric field component, or you can express it in terms of its magnetic field component. All right, that's just remember, S is the intensity. That represents the amount of intercepted power. That's what it means. Amount of intercepted power, that's the amount of power which is going to be intercepted by any surface area or cross-sectional area. All right, so the energy density of the electromagnetic wave multiplied by the speed of light is going to give you the amount of intercepted power. That becomes the intensity of the electromagnetic wave. All right, all right, so this is the definition of intensity, right? The amount of energy electromagnetic wave transports, amount of energy transported by the electromagnetic wave per unit of time, per unit area is the intensity by definition. All right, take a break for 10 and then we'll continue. Okay, so it says it's a quiz. It's actually a problem. Okay, so this is in reference to the cell phones that we were talking about. So the frequency range is given. So it's going to be 860 to 900 megahertz. Power output is also given. So it's going to be 0.6 of a watt. And there's an antenna that's going to be 10 centimeters long. It's a little bit over, it's about 3 inches, I think. So it says find the average magnitude of the pointing vector pointing vector in this case is going to represent the intensity. All right, so it's going to be 4 centimeters from the antenna. That's like almost an inch and a half penetration into your brain. So that's what we're looking at. And then, so we got a maximum exposure standard that we end up getting from NSI, which is considered safe. So we have that number expressed as almost 6.7 milliwatts per square centimeter. So that's the intensity. That's the maximum exposure, which is considered safe. All right, so the question is, when we do the computations for intensity, so that's the pointing vector is going to give us the intensity, about an inch and a half into the brain. So what is the amount of radiation intercepted? So what is the intensity? Intercepted power by the brain, like an inch and a half into the brain. Let's see if that's actually. So, hold on. I made a big deal out of it. Just want to make sure that we got the solution somewhere. All right, I don't see the solution there, but I'll show you where the solution is. All right, so
here
the
at the Air Force Research Laboratory in the sunny Mojave Desert, they're working on solar propulsion. The pressure of sunlight on solar panels could push ships through space, or the light could be converted into power for electric motors. Or an inflatable solar concentrator like this could heat the propellant in rocket engines. This would allow for rocketry, but with much lighter fuel and much more efficiency.
So the solar cells. Okay, so let's talk about radiation pressure. Okay, so force can be described in terms of force causing on the mass is going to cause it to accelerate, right? That's one way of looking at it. There's a second way of looking at it. The second definition of force is how fast the momentum changes in time. Okay, so we talk about momentum in physics 1. P is going to represent momentum. So when there's a force acting on something, it changes the momentum of that mass. Okay, so that's the meaning of it. So the motion changes because of the force. This is the Newton's second law expressed in terms of change in momentum. Put differently, force acting on the mass is going to cause it to accelerate, while momentum is a combination of mass and its velocity in essence. All right, so Maxwell came up with this expression. It tells you the change in momentum. It says the change in momentum is going to be related to the ratio between the amount of energy that's being transferred per speed of light. All right, so somehow Maxwell comes up with this expression. I'm not entirely sure how he came up with it, but this is the expression that we will get to use. All right, so you guys are taking college physics. D is the same as delta. When we use D, which means that the change is very small, so all of a sudden we end up using calculus as a result. So we're not going to use calculus. It's the same definition. So how fast the momentum changes in time, which means that the force changes momentum in that certain time period. So the change in momentum is related to the amount of energy carried per light speed. So this is what Maxwell came up with. All right, so the wave transfers, obviously it transfers energy. The amount of energy transferred by the wave divided by the light speed is going to tell you how much momentum is going to be transferred in essence. All right, so that's the transfer of momentum. So if we take this and do a back substitution into that formula, so we can come up with an expression in terms of the amount of force which is going to be generated by the electromagnetic wave. So which means that this is the amount of force which is going to be transferred by the electromagnetic wave in essence. All right, so when you're looking at this expression, this is the amount of energy per unit time. So the amount of energy carried per unit time becomes the power in essence. So we can take that expression. So this is the amount of energy transferred per unit time. So that's your power. And force divided by area, this is the amount of force intercepted by area. A certain amount of area gives you a pressure. So which means that both sides will be divided by area. So when you divide both sides by area, here's what you get. This is the amount of energy per unit time intercepted by this area. Is going to give you the intensity in essence. All right, so on the left-hand side, we have the radiation pressure or pressure in general. So that's the newtons per square meters. On the right-hand side, you have the energy, you got the time, you have the intercepting area. So the amount of energy per unit time, per unit area, that's the intensity. So that's the intensity divided by the light speed is going to give you the radiation pressure in essence. So that's the meaning of it. So that's the amount of pressure which is going to be generated by the radiation or the electromagnetic wave. That represents the intensity. Speaking of the intensity of the electromagnetic wave, There are two kinds. One is the reflected intensity, the amount of intensity generated by the reflected light or the electromagnetic wave, and SI represents the incident intensity. All right, so what is that supposed to mean? I'm hoping that I have some kind of an explanation for it. All right, so this is known as the radiation pressure. All right, so the intensity, okay, we gotta use a little bit more than that because I'm not engineering students. All right, so here's the reflective surface. All right, guys, this portion is the reflective surface. The back of it is non-reflective surface. So what's happening is we will have the incoming ray, so it's incoming in this direction. All right, so this is known as the incident electromagnetic wave. So it's coming in. This one is incident, I, and then it gets reflected. All right, so this one is I, and this one is R. This one is reflected. All right, so the radiation pressure is the total intensity. So you're looking at the intensity incoming or incident ray plus the intensity of the reflected ray, in essence. And so divided by the light speed is going to give you the radiation pressure. All right, so it was unintentional, but let's go back. Okay, so from a conceptual perspective, what does it mean? Newton thought that the light was composed of particles. His argument was that the waves cannot transfer momentum. Guess what? He was wrong. That's what it means. Light is an electromagnetic wave. It can also transfer momentum. Okay, it creates a radiation pressure. It can transfer force. It can transfer momentum, which means that the radiation pressure generated by the sun can push the tail of a comet away from the sun. That's what it means. All right, so Newton's argument. All right, so by definition, the force per unit area, the amount of force intercepted by an area, is called pressure, right? If it's generated by an electromagnetic wave, it's called the radiation pressure. So the electromagnetic waves not only transfer energy, they also transfer momentum. All right, so how fast the momentum is transferred is known as the electromagnetic force, in essence. So the amount of force divided by the area is going to become the electromagnetic pressure, radiation pressure.
30 years ago, space was considered a vacuum, except for a curious clue. The tail.
So Huygens argued that the light was composed of waves.
Your mic goes fuzzy again.
All right, give yourself 5 points for that one. So Huygens is the one who suggested that the light is composed of waves, right? And then Maxwell bought into the idea because Faraday was thinking that the light was composed of electromagnetic waves. Newton's argument was that the waves can only transfer energy and they cannot transfer momentum. All right, so the particles through collisions can transfer momentum. As it so happens, he was wrong. The waves can not only transfer energy, they can also transfer momentum. And that's it. So that's what he came up with. All right, so the evidence that the electromagnetic waves carry momentum is the tail of a comet points away from the sun. A is the best answer. All right, so we got a company claiming that they developed a material that can absorb light without transfer of momentum. At this point, you know it's impossible, right? Okay, so light not only transfers energy, also transfers momentum. So it would be impossible. Okay, this is just for the hell of it. It's kind of weird. The reason why I'm gonna have this discussion, I'm just doodling at this point because I'm trying to figure out what Maxwell did. Remember, if you go with the argument that Newton had, this is the amount of energy which is being transferred by the electromagnetic wave, right? Maxwell somehow, I don't know how he did it. I have to find the way he came up with it. Normally, in preparing these lectures, I study the history carefully. I also put myself in the shoes of these people who are trying to solve these problems. It's because it's a lot more interesting to approach it as a puzzle and then try to solve it my own way. And then obviously physics is a lot more advanced today. So what took him years to figure out, you can figure out within 5 to 10 minutes normal, okay? with the classical physics, that's the way it is. I look at it, I say, oh, this is the way they were thinking about it back then. I understand it. Okay, but there's something puzzling here because this is the amount of energy being transferred by the electromagnetic wave. I'm looking at it. And somehow it takes the concept of energy. This is the amount of energy transferred per unit of time. All right, and then this is the change of momentum per unit of time. So this would be the force expression that I'm looking at. So the times cancel out. So eventually this is what you come up with. But the weird part of it is, how did they know that you would take this expression, the amount of energy transferred by the electromagnetic wave, and divide it by c? Okay, so I don't have a really good explanation for it. This has to be a derivation from somewhere. You can't just pull this sort of stuff out of your butt and just put it on paper. Well, what's weird about his discovery is, guys, the change of momentum, or the momentum of light, is this is the speed of light, and this is the mass expression of light. Okay, whatever that means. This is going to make sense to you when we get to it. Which means that this is going to represent the inertia that light has. All right. All right. So if I express the momentum of light in this fashion, and this is the amount of energy carried by light, which is E, everything is divided by C. Notice that if you solve for E, you end up getting Einstein's famous mc squared, E equals mc squared equation. So it's so weird that Faraday somehow stumbled onto this equation before Einstein. And you got to remember, Maxwell was Einstein's hero, right? Because I was just thinking about it, because I was just trying to figure out how Maxwell came up with this original equation. This is the trick. I'm not sure what he was thinking, but this is what he was able to put on paper. And whatever he was thinking, all of a sudden with very little adjustments. If you consider light as a particle, all of a sudden you end up getting E equals mc squared. He's thinking that the light is a wave, so the wave expression would look like this, and then the light expression, particle expression of light would look like this. This is kind of weird. Anyway, so